So good evening everyone and welcome to today's session of Saturday Talk by JanyuTech. Today we have Professor Dr. Aditya Paranjape to deliver today's session. Since he's repeating quite a few times on this session series, but still a brief biodata about Aditya. Professor Aditya Paranjape received his BTech and MTech from IIT Bombay in the year 2007 and his PhD from University of Illinois in the year 2011, all in aerospace engineering. He is currently working as Associate Professor of Mechanical and Aerospace Engineering at Monash University in Melbourne.
Good afternoon, everyone, or good evening, depending on where you are. So I'm pleased to be back here. I want to talk to you today a little more about my research. So in the previous two talks, I remember I spoke once about, I think about the evolution of the Bellman equation in one of the earlier talks. And then I also talked once about the classes of problems in multi-agent systems. So those were fairly high-level overviews of the subject areas. So today I thought I should talk a little more about what I've done in the past few years. And some of it, of course, is very relevant to what Janyu does, including some areas where I've been trying to collaborate with Janyu. So here's a brief outline. So I'll start by presenting sort of canonical problems in task assignment. The idea here is to show you that robotic task assignment is not just about robotics, but it's a very general class of assignment problems. In fact, a class of what are called as combinatorial optimization problems. So I'll just give you a little bit of an overview of that subject area, as it were, and then I'll go straight to two bits of research that have been going on for the past few years. Interestingly, the first case study doesn't actually deal with robotics per se, but as I'll show you, the problem statement has a very intimate relationship with our robotics applications as well. But what it serves to do is to illustrate one family of methods that are used for task assignment. In the second case study, which is also ongoing, I'll talk about a class of problems known as coverage problems. And coverage problems are actually a class of task assignment problems. Although they go by two different words or two different descriptions, you will soon see what the relationship is between those two areas. Okay. Now, I want to give a little disclaimer here. I was hoping to put together a single presentation that hasn't gone down very well because of how my time worked out, or rather how I managed my time. I didn't do a great job. I remember someone once talked about time management on this forum. I should have taken their advice a little more seriously. So what's going to happen is, for that second case study, I'm going to turn to a document that we have prepared elsewhere. I mean, part of the problem is I'm currently using OpenOffice, but the slides are prepared for case study 1 in Microsoft PowerPoint, for case study 2 using LaTeX Beamer. So kind of putting it all together is really very difficult, but I'll try and do the best I can. So apologies if I miss out anything in the process, but I hope this session will be interesting as well as instructive. And of course, I'm very passionate about the subject area. So at some time I may start to go a little off tangent. So just please do stop me if I do. All right. Okay, now those figures should have not appeared this way. These are fairly big figures. So let me go back to the original presentation. Okay, I think this is probably much better. Saves us the trouble of, okay. So what do we have here? So we have this class of canonical problems which go under the umbrella of combinatorial optimization. So to start off, let's consider a very simple setting where you have n robots and n tasks. So same number of robots as number of tasks. And we are going to assume that all of the tasks have to be assigned in a single shot. So it's a one-off assignment, just one round of computations that has to happen. And the hope is that we, in the process, end up maximizing some notion of utility. So what we mean by utility is this. So when a robot J completes a task K, or we could say when it's assigned a task K, it gets a utility A sub JK, all right? Now, the place where we talk about robots other than humans is that this utility AJK does not depend on the tasks that have been assigned to other robots. Now, if you look at humans, we know how this fear of missing out of FOMO works. If somebody else gets an object that you covet, the value of that object suddenly shoots up and the object that you've got suddenly becomes less valuable. That doesn't happen with robots. We assume that this AJK is only a function of the robot and the object. It doesn't depend on any of the other assignments. And what we want is to find an optimal allocation policy. So a policy P allocates to every robot J some task K. And what we want to achieve is a maximization of the utility, which is written like so. A summation of A, J, Pj, and you want to maximize it across the entire body of robots. Okay, so this is a fairly straightforward description. And the way it's written out, what you'll immediately realize is that these robots and tasks could have just been people and objects, for example, or could just be two arbitrary sets. And that's what makes this problem so universal. Now, this simple problem actually encapsulates a lot of practically useful settings, but some generalizations do occur in practice very often. The simplest generalization is where you have non-square problems. So the number of robots is not the same as the number of objects. I'll show you an example when we go to the first case study. A second generalization, which is actually far more serious in nature, is where you have centralized versus distributed assignment. So when we talked here about n robots and n tasks, the way I described it, I just pretended as if there was an oracle, or what we show in this figure as a shared memory, which has access to all of these utility functions, and it's able to, using some method, solve this optimization problem. Okay, we just assumed that. But in most practical settings, that central shared memory or oracle does not exist. What you have is a network system such as the one that's shown here. So you end up with having to solve that same problem with limited information or with delayed information, because if you have a network system, it takes time for information to flow from one end of the network to the other. So that creates a slightly more complex scenario to solve the problems. The other set of problems we encounter very routinely in practice is where these tasks, I told you that the task here is assigned in a one-off manner. Well, what we find very often is that these tasks don't arise simultaneously. They arise in a sequential manner. So if you look at this figure on the right, you have task 1, 2, 3, all the way to M. And the way these blocks are drawn, as you go right, you go forward in time. So these tasks all arise at different points in time. They come with temporal constraints, which is to say that these tasks may require different amounts of time to solve. And moreover, these robots may not be all identical. The tasks may not be all identical. And that's what these colors show in here. So these are all generalizations of this very same assignment problem. So where are we at with respect to solving this set of problems? So again, I'm going to just show you some canonical solution techniques, not show, rather just tell you about them now, but illustrate some of these using the two case studies. It turns out that the task assignment problem is fundamentally a combinatorial optimization problem, and linear or integer programming methods work very well in a fair number of cases. All right, so that's the default method that you should turn to if your problem permits a fairly simple description. So if you have well understood theory, well understood guarantees, well established solvers as well. However, it turns out the set of problems where you can use LP or IP are limited. In particular, these methods work best when you have shared memory. The moment your information starts to be dispersed, you end up having to introduce some heuristics or hacks into the problem. So that's when these methods don't always work best. What works well are a family of iterative assignment methods, and specifically one known as auction, which I'm going to show you very briefly in the first case study. The name auction, of course, suggests a standard economic auction, and that is where the motivation came from for these auction methods. But these were developed specifically to solve the assignment problem in the form that we just saw on the previous slide. So I'll show you that illustration in the first case study. And what's nice about auction is that unlike the other methods which work on shared memory, there is a very elegant extension of auction to network systems where the memory is distributed. And that was done in this paper in 2008 by Zavlanos, George Papas, and a few other people based in the University of Pennsylvania. All right, so that all works for basic assignment problems. The moment you have these problems where there is the tasks are sequential, there are temporal constraints, there is heterogeneity in the problem, these first two families of problems don't always work well right out of the box. They require a lot of hacks. So what works well in here, and this is something we've also seen in the industry, incidentally, are heuristics. So what we mean by heuristics are rules that maybe you've learned from experience, or some of these rules are intuitive. For example, first come first served is about as simple as it gets. But what we know from our experience is that these heuristics with some refinement by domain experts do a perfectly good job. They are not fully optimal. In fact, the reason why they're called heuristics is because they are not exactly solutions to that problem we saw on the previous slide. It's just that as a post hoc analysis, we can go back and argue that some of these heuristics come to within 20 or 30% of the optimal solution, as an example. But that comes after the fact. What's also working very well now are methods based on dynamic programming and game theory. Dynamic programming would be more familiar to people here in the form of reinforcement learning, which is also referred to sometimes as approximate dynamic programming. And again, we've got some experience using ADP as well to solve some of the sequential problems. At the very end of this talk, I'll give you my take on where these methods stand. So I don't want to discuss these any further, but let me jump straight into the case studies now. The idea here was only to tell you again some key names or key methods that you can always use for your problems. But I'm going to illustrate auction as part of case study 1. And once we go to case study 2, you will actually see some of these nice heuristics in action, and you'll also see automatically what sort of limitations come with heuristics, how they scale up or why they fail to scale up, and maybe we'll just talk about what can be done to make them work. All right. So the first case study will talk about the problem of allocating landing slots at airports. A landing slot is a small window of time that's given to an airplane to touch down on the runway and exit the runway. That's the definition of a landing slot. Typically, these are anywhere between 45 seconds to 1 minute long at major airports with standard commercial services. Now, if you had to look at this problem in purely technical terms, this problem is more of a queuing problem. So you have a single server in some sense, namely the runway, and you have multiple queues. I'll show you what I mean by multiple in this case, but you can think of the arrival airplanes as creating queues. The analogy, however, as we will soon see with this business of task assignment, is that this problem is similar to allocating sequentially arriving tasks to a set of robots. And I'll tell you what the set of robots are in this case. So the analogy will become clear in just a moment. And this material is we sort of published this fairly recently at a conference known as a Winter Simulation Conference. So this is something I did with one of my research engineers in TCS research, and a system version of this is currently pending with the Indian Patent Office. It's in fairly early stages. So let me show you how auction was brought to bear on this problem. First, let me give you a bit of a background of this problem, because that's where a lot of interesting things happen. So I'm pretty sure you've all flown commercial flights, so don't have to talk much about it, but what you'll notice is, here's how the arrival sequence works. At the end of cruise, you descend initially from the cruising altitude. You're then put into a hold where the plane basically loops around in a small area. Especially when you land in Mumbai in the morning or in the evening, you'll end up doing at least 2 to 3 of these loops. And if you pay attention to the altitude readings, you don't get them very often in Indigo. Indigo doesn't have the entertainment screens. But if you're on Air India or Vistara back in the old days, you could actually see the altitude in real time. And these loops happen between 10 and 7,000 feet. Once the airplane exits the hold, it goes to this point known as the final approach fix, or a FAF, and this FAF is about anywhere between 8 to 15 nautical miles from the airport, from the runway, and at this point the plane's altitude is about 3,000 feet. So from here on, it's a straight stable descent to the arrival runway. Now as of now, this entire process is managed by human operators in the local air traffic control unit, and the standard approach that they use is first come first served, and that's the way they interpret fairness. Okay. Now, here's the interesting thing. When the plane descends, it's not consuming a lot of fuel. I think that's fairly obvious. Your engines are fairly silent. They're not set in any high thrust mode. But this holding itself is actually fairly heavy in terms of fuel consumption, because while holding, the plane's maintaining altitude, and that too, it's not doing it at an optimal speed. So in terms of fuel consumption, the better you manage your holds, the better it gets. So why is this a challenge? Well, at most international airports, so here's a map for London Heathrow, by the way, you have multiple holding areas. You remember I used the phrase multiple queues earlier. So for example, for Heathrow, for one arrival runway, so it's an east-west arrival runway, so 27, you have 4 holding areas, which are shown out here. And these areas correspond to different geographical regions. So when you go to Heathrow, for example, flights coming from India will typically go to the Lambton stack. From Europe begin, from US and North America could go to Bovington or to Auckland. And all of these planes have to be then routed to a single fixed or final approach fix, which is located 10 miles out from this particular runway. All right. Now, the only time you make an exception to the first come first served rule is when there's an emergency, all right, or if there is a problem with load management in these stacks. So it turns out you can't go to arbitrary altitudes in these stacks. These are maybe about 10 to 15,000 feet high. So if there's a problem, they will start routing some of these stacks with priority, but that is about it. So either an emergency or load management is the only time you will move away from FCFS. And the problem with FCFS is something like this. If some of you have seen the older, let's look at Indigo, because you see a lot of Indigo airplanes in Mumbai. If you see some of their older airplanes, they have smaller engines, they have that very typical triangular winglet. Engines are noisy and they are very fuel hungry. Fast forward to A320 Neos, which Indigo has ordered in large numbers now, they are very fuel efficient. So the question is, if I had to keep 2 airplanes in hold, which one would I rather keep? The principle of fairness is I'll let that fuel intensive airplane stay longer if it comes later. But if I have an imperative to minimize emissions, especially because if I have a lot of traffic, I mean, Heathrow handles 50 odd airplanes every single hour for 12 hours a day. It then makes sense to think about, well, can I allow the more fuel efficient airplanes to go through, or maybe, sorry, my bad, other way around. Can I have the fuel efficient airplanes hold a little bit longer? And if I have to make them hold longer, how do I make it fair for them? What do I give them in return? It could be money, it could be landing rights, it could be reduction in aircraft landing fees, it could be anything. But what's a fair reward that you can give to an airplane to stay a little bit longer just because it's fuel efficient? That is the that's the problem that we were looking at. The idea, of course, being We want to minimize the emissions profile at these airports. All right. So I've already walked you through the terminology, so no need to go through that. Here, but there are some interesting numbers for how fuel consumption works. I told you about the Airbus 320. Look at this. There's almost a 10% difference between the old airplanes and the newer version. If you go to bigger airplanes, 787 Air India has almost 27 of these, more coming. It's twice that of the Airbus. And if you go to the old 777s, it goes up even further. It's almost 20% hike. We thankfully have phased out Boeing 747s, but some airlines like Lufthansa still use them. And you notice it's almost a doubling in the amount of fuel consumption. So really, and by the fuel consumption eventually translates to emissions. And these old airplanes, by the way, don't just emit in proportion to the amount of fuel. They also emit just because the older technology is such. So NOx emissions, for example, are way higher compared to current airplanes, everything else being normalized. So it really makes sense to keep these airplanes in the air for as little while as possible. And okay, these have to be held a little bit longer. So here's a problem statement for us. We want to allocate arrival slots at the final aircraft, at the final approach fix. Now remember, I told you about arrival as a process at the airport, but once the airplane is at the approach fix, it's committed to a landing. So you might as well deal with how you allocate airplanes at the FAF. And we want to design a fair economic reward that we can give some of these more efficient airplanes for staying in the air a little bit longer. So how does this work? So we use an auction-based scheme. This auction again will look very much like a standard auction, price-based. But what's actually happening under the hood is a straight-up assignment problem. I hope in all these slides I'll be able to show you how it's done. So here's an overview before I go into the details. The allocation looks to minimize the total fuel consumption of the airplanes that are in the holding area, and in the process, it's also going to compute fair prices for the slots. All right. Thereafter, these prices are going to be adjusted using a second linear program to ensure that airplanes that are environmentally friendly are actually given some credit rather than a penalty being imposed on the heavier airplanes. Penalties don't work commercially. Pretty much every airline would protest at it. But if you give some other airlines some freebies, chances of a protest are fairly minimal. But now, remember I told you that these methods don't work in a native vanilla form when you have sequential queues. And the way we deal with it is using replanning. So what we'll do is we'll plan for a short window of time, and when we've covered a subset of that window, we replan. That's how we deal with sequential queues using methods like auction. So how does auction work? I think this is the interesting bit, and these methods are very implementable as well. So let's assume that we have a non-square problem, n bidders, and we have m objects, all right, m being bigger than n, and the understanding is that every bidder gets at most one object. It's possible the bidder may get none. So the way to understand this is you have n airplanes, m slots, and every airplane will get at most one slot, and some airplanes might even have to hold a little bit longer. We are going to assume the process is centralized for now. So what's actually happening under the hood is that all of the information about the airplanes is relayed to the ATC, to a central server. The auction is run on that server, and from there on, slots are assigned and rewards are computed. So inside this server, every airplane is seen as a bidder. Okay, so every bidder I assigns some value which we call Vij to an object j. So this notation sometimes changes. That Aij that I showed you earlier was exactly Vij. This is what we ended up using in the paper for whatever reason. And this Vij, you can see, because it's two indices, you can assemble a single matrix V using these Vijs. Right. In our setting, this Vij is the amount of fuel consumed and just a negative sign to make sure that the max min business works correct. Now, the optimal assignment problem is that we want to minimize the fuel consumption, and because we have a negative sign here, we want to maximize this particular negative quantity. Right. I is the bidder, and A of I is the slot assigned to the bidder. And in the process, we want to compute an optimal price. For the moment, we'll call it a price. Later on, it will actually be some form of a credit. So it will be a negative price of sorts. And we want to compute the optimal price so that it satisfies this particular condition. If you look at this condition, V minus P is like a profit. So the idea is the slot assignments have to satisfy the condition that every bidder should feel like they've got the best profit for their deal. All right. So for example, in this case, if you assume some object J being assigned to the bidder I, and this profit were bigger than what it gets here, then that's not a fair assignment. So this is a property that also has to be satisfied by our optimal prices. Now remember, these prices are something that we haven't yet solved for. We haven't even told ourselves what these prices are. And the nice thing about auction is that these prices actually come out as part of the solution of the assignment problem. All right. So the way it works sometimes is that you start off with an arbitrary price, and then you go through a standard iterative bidding process. The prices are hiked using a certain logic until they settle down. Now, this idea of bids and prices works perfectly well when you have a positive reward and a positive price. We don't want that. We actually want to eventually give away a credit. So we want the price to be negative. So to compute that, it turns out you have to run a second linear programming problem. I won't bother you with the details, but if you're interested, you can look at something known as the complementary slackness condition, which is actually this property here, but you solve this particular profit maximization problem directly and impose some condition on the prices, and the solution, it turns out, gives you the amount of credit to be given to the airplanes directly. All right. So the second case study was distributed coverage. All right. So by coverage, what we mean is area partitioning. So you have a physical area, a patch of forest, a patch of desert, and you want to partition that area between n robots so that each robot surveys an area. If there's an event in that area, for example, if it's looking for a human, or if it's working on disaster relief, it needs to find victims of the natural disaster, it's going to find them, give them some package or give them medicines, and that's how it's going to complete its task. So the question is, what area do you assign as an area of responsibility to a given robot? That's the larger problem. And here the problem is something like you have a large number of tasks. This is the analogy, and these tasks have some special map in them. All right. This is a little abstract, but what you're going to do is you're going to assign tasks to every robot in one shot. So that area can be looked at as a collection of tasks. And with that, what you're saying is you're going to complete tasks in some sequence until you get to a special task, at which point you respond and you pull out of the system, as an example. So that's the analogy between the coverage problem and a standard robotic task assignment problem. Sorry, this paper, I got the citation wrong, but this was a paper that we also presented in 2023 at a conference known as AMUS. This was with a student of mine also at Imperial. Now here I'm going to take the liberty of moving to a different document, and I hope that document is going to be visible to you. I won't bother you with any of the equations. I'll show you figures and tell you what we were trying to do in the coverage problem. Let me put fit with, yeah. All right. So what's going on here is something like this. You have an area. In this case, our environment is just this little square. You have a bunch of robots. Here we have 8 robots, and this blue region now needs to be partitioned between these robots. Okay. That is it's as simple as that. Now the way we do it is, it's not just that we want to partition these areas, but it's an assumption. In this particular instance, all of these robots are trying to detect just one event. All right. Not events in their individual areas, but a single event. We don't know exactly where that event is going to occur, but what we assume we know is a probability distribution function for the occurrence of that event. So for instance, if it's normally distributed, we could say that with a high confidence that in the central region here around 1,1, you have a high probability of the event. And as you move away from the center of the environment or the center of this region, the probability of the event occurring starts to drop down. All right. So what you want to do is to assign areas of responsibility to every robot, but weigh it in some sense with respect to this PDF. Now this problem was first posed towards the end of the 1990s, and one of the first seminal results that came out was in 2007. It was from a group in the University of California, Santa Barbara, and here's what they came up with. So they said, all right, let's start with n robots. Here it's 8 robots. We'll assume that all robots can communicate with each other, although we don't actually need, as it turns out, all-to-all communication. And all that each robot will do is that it will draw these things known as Voronoi partitions. So what do we mean by Voronoi partition? Well, it is something like this. Inside each of these cells, the property that each cell satisfies is that every cell is closest to the robot that it is assigned to. So if you look at this cell that I'm trying to highlight with my mouse right now, what it means is that every point in this cell is closer to the robot as compared to every other robot. So this is another Voronoi partition. And once you have the Voronoi partition, you can locate its centroid. The robots go to the centroid and they keep running this same process. And it turns out that what you get in the end, if you weigh these Voronoi partitions with that PDF, is an optimal partition, which maximizes the probability of detecting that event in the shortest possible time. So this is what we also kind of just experimented with a little bit. And yeah, sure, obviously it works pretty well. This was all established back in 2007, 2008. Where is the problem? The problem is with communication. If you look at this business of Voronoi partitions, although I said, it's all-to-all communication, what really matters is communication between neighbors. And what we mean by neighbors is a robot is said to be a neighbor of some other robot if their Voronoi partitions share an edge. Okay, so it's an adjacency map that you will draw, and based on the Voronoi partitions, that can change as the partitions develop, but you at least need to ensure that you can communicate with all of your neighbors. The problem is what happens if your communication is sporadic. So if you look at this region right now, what happens if this region is really very large to the point where these robots can't communicate over Wi-Fi or over Bluetooth? What happens if there's GPS jamming in this area, or what happens if radio is jammed in this area? At that point, in the absence of global communication or even neighbor to neighbor communication, this kind of a scheme absolutely does not work. Now remember, the Voronoi Voronoi partitions are a solution to the optimal control problem of partitioning the area. So if that doesn't work, we then have to turn to something else, and that something else, it turns out, are heuristics. Okay. So what's the heuristic? The heuristic is, well, in our case, we've been experimenting with several of them. I mean, I still have some students working on them right now. But the heuristic that this particular student looked at in his time was when robots enter the environment, they don't know how many other robots are in the environment at that time. They just know that it's a team of maybe 8 robots that's going to be in the environment. They don't know how many exist. And every robot takes up a share of the environment that it thinks is a fair share. So I've shown you 2 examples based on our work. Some other examples, we've also tried these out in drones, by the way. We participated a few years ago in a competition in India where we developed auction-based methods for task allocation for about 10 drones, and we didn't deploy it in practice, but we came very, very close to deploying them on our final solution. So we've got some field experience. These methods work beautifully on the field as well. So where are we at as a field now? So task assignment as a field, I would say it's in this territory where the easy 85% has been done. And when I say easy, I don't mean trivial. I just mean that this is the easier bit. So I should say easier 85% done. The hard 15% remains. So what has been solved? So we have decent heuristics like greedy methods, first come, first served. And the best part is, for those simple heuristics, in a lot of cases, we have guarantees. So we know how close they come to optimal solutions when they do. We know when they can fail as well. Moving away from heuristics, we now have a great suite of solvers for ILPs, for integer and linear programming problems. The solvers like Gurobi, for example, are robust, they're deployable in practice, and they've been tested in like scenarios with hundreds or thousands of agents as well. So we know they work very well. That's one of the success stories of combinatorial optimization. Over the last maybe about 10 years, solutions based on dynamic programming or reinforcement learning in the approximate sense have been maturing pretty well. So again, we've got experience using these in settings involving robots in sorting centers. We've got some experience with robots that are used for packing. We've used the same methods for scheduling the crude movement inside refineries. It's a very similar looking assignment problem. So we know these methods are maturing fairly well as well. So that's the 85% I was talking about. What's the 15% now? 15% in my view is this. We know from experience, again, from talking to some of my colleagues and friends who work in this space a little more as professionals as compared to me. One thing we know is that these learning-based methods, although they do reasonably well, are still not able to beat principled methods that are developed by expert humans. In fact, in some of these competitions that happen every year where they try learning and heuristics on problems involving a large number of agents or a complex industrial scenario, these principled methods still beat learning-based methods hands down. There are exceptions like chess, of course, where we know that AlphaZero is like miles ahead of the humans. But in real industrial problems, human experts can still beat learning-based methods by a mile. The question is, why is that happening? Because at the end of the day, we are solving the optimal problem directly. We aren't resorting to heuristics. So what's going on under the hood? That is still, in my view, an open problem. The second set of problems that are open to a great extent, although they have been tackled again to a limited extent in this 85% category, but they are still in the 15%, is guarantees in the presence of communication problems. So I already showed you one set of results on how you deal with minimal communication when robots do task assignment. But what happens if that communication is faulty, error prone, or even worse, adversarial? So you have an adversarial agent who deliberately obfuscates information, who deliberately adds faulty information into the mix. How do you deal with that when you do task assignment? So these are the more open problems right now. And again, some of these are very much relevant to the industry as well. So my guess is maybe another maybe 5 or 10 years, we have some exciting research in front of us. After that, this is going to again be a solved set of problems with solvers on lines of what already exists for ILPs and such. So with that, let me stop and I'll take your questions. And again, I apologize for the fact that this presentation had to be a little ad hoc. I had to bring together slides and a separate document. It's not very nice, but that's the best I could do with my time constraints. So thank you very much, and let me stop sharing for now.
Why you are not considered max min or min max type of solution, or it will become a game theoretic approach? What is the reason you are not considered max min approach?
Because that approach, I mean, the problem formulation never went in that direction. So usually we would do min max kind of an approach if the problem formulation goes there. But our problems never went in that direction. So for example, I just talked about this charging problem right now. People have tried min max formulations there, but it's somewhat contrived, if I may put it that way, because these robots are not trying to compete with each other. at any point. In fact, all that we're trying to do is just replace the oracle with a distributed logic. So as a result, I think that's the best answer I have.
For the answer.
Our problem formulations never went in the min-max direction. So in fact, even when we use these techniques, the first thing we do is we write down the problem fully, and then depending on what the problem looks like, we try and map a technique to it. So at no point did our problems end up in that space. But having said that, I'm fairly familiar with people who apply game theoretic methods as well to task allocation, especially if it's multiple robots. They try and pose it as a competition, and it seems to work okay at times.
No, Aditya, I have one question. Actually, besides robotics, India is now in a very grave situation as far as the train collusion software is there, which is known as Kavach in India, which is very essential for avoiding any train accidents. So, whole of India is struggling to make a Kavach which is robust enough to deal with all possible situations. So, I know robotics is a different type of subject, but can some work be done on that? Because a lot of people are trying that. Last 3-4 years, there is a lot of publicity about it and it's working, but on ground it's not really picked up to be really safe for the entire country. So we think of sort of addressing this in some way? Because
we certainly can. This is one of
the gravest software challenges in India today, and none of the Indian top companies are investing into this.
Okay. So in fact, remember I told you a while ago about competitions that are run annually, where heuristics, like I said, have been shown to do way better than some of the learning-based methods. One of the competitions 3 years ago at one of the premier conferences actually featured railways. That is getting railways to move optimally between a set of sources and a set of destinations, and to do it without collisions and plan their, I think, their arrival, departure, and halts in between, because they were the routes were overlapping. The question was, when do you allow a certain train to go on a certain section of the track if there's a competing bid for that same section of the track as well? So absolutely, it's one of the well-known use cases in the CO field.
But any software across the world cannot be actually sort of changed for Indian conditions. No? I think India may be a different type of boundary limit. So you have to tailor make a software here.
Oh, absolutely. No, I'm not saying that the solution exists as a software which we can take directly, but there is like, for example, all of the competition entries that have been happening so far in their own right are fairly strong contenders for that eventual solution, which the Indian solution can eventually be based on. So it's very much an actively probed use case. Mm-hmm. But I
don't know why Indian software companies are not putting the resources into this in spite of government pressure. So there's a lot of government pressure to build this, but somewhere it is not happening in India.
No, it's not easy because the ticket prices are very low. The amount of money you get, and apparently, completely what I heard from some people in the software industry, not like a very first-hand account, is that the bidding process is extremely complex for them. So the amount of money they stand to lose on that bid is prohibitive. So they'll just try and stay away from it.
That could be the reason.
That's usually the reason. So they say, if it's not, so companies like Infosys or Wipro will be like, if it's not on the order of a few 100 crores, I don't want to waste my time and money getting into a bidding process.
I have talked all of them on this. I have talked to all of these companies on this. They show initial interest, then they walk away. So I think this could be the background reason.
Yeah, that is usually what I've heard as well. So because when I was at TCS, I tried to get them interested at different points of time in working with government projects. Nobody ever said this, but that's the same impression that I came back with. So certainly, thank you very much. Thanks for having me here.